Hi, welcome to another episode of ProofPilot. We are here to talk about subspace topology. Now we have reached the third chapter of the Introduction to Topological Manifolds by Lee. And in this chapter, we actually see that we can create new topologies based on those topologies that we had in the past. And one of these topologies is actually the subspace topology. And here is what we here's what we call a subspace topology. So let X be a topological space and let S be a subset of X. Okay, just any subset, it doesn't matter what kind of subset is. And then we define the topology on S by these definition right here. Okay, as you can see, you just take all those open subsets that you had in the original space X and then intersect those with your subset S, and then you call these new things as the open subsets of your new topology. And we call this topology the subspace topology. But another important note is that we still need to prove that this is in fact a topology. As you can see, we are saying that this is a topology, but we just defined it. This is just how it works. So we need to uh, verify that this thing right here that we uh, defined is in fact a topology. So we had three conditions to verify what is a topology. The first one was that the space itself and the empty set should be open sets. And the space itself right here is S, and the empty space everywhere is just the empty space. Now I have to show that these things are open sets, so they belong to our topology. And the way we do that is we just intersect S with X. As you recall, this X itself was an open subset. Okay, the X itself was an open subset for your original space. And this thing would be equal to S, and S intersected by the empty set would be equal to the empty set. So here's the first condition satisfied. The second condition was that you could, let's just do the third one because the third one is easier. The third condition was that they are closed uh, under finite times of intersection. So I'm just going to do for two of them, and then by induction we can say that this is true for n number of times. So let's suppose that we have u1 and u2, and these two things belong to our topology. Now I have to show that u1 intersected by u2 belongs to the S also. The way we are going to do that is just use the definition of the open set. So just let's see what this meant right here. Okay, what was U1? It was the intersection of S with some open subset in X, which we call V1. And let me just write the intersection again. And U2 is similar, so we call this S intersected by V2, and just take the S out, and as you can see, this would be equal to S intersected by V1 intersected by V2, and this thing belongs to your original topology, and this would be an open set. So S intersected by an open set will be an open set in the subspace topology. The second one, which I'm going to prove here as the third one, was that they are actually closed under arbitrary, infinitely arbitrary infinitely arbitrary unions. So if I have a collection of open sets and I'm going to call them U alpha, and the alpha is just belongs to some uncountable sets, then these things should be in our set. And again, this is pretty similar, and this is just a fact from set theory, that if you just write the definition of this thing, it would be the intersection of some let's call these things beta, and beta is just in some sense I prime, then again by these thing being in the topology Tx, then this would be in Tx, and S intersected by an open set will be an open set in your subspace topology. So we have now verified that this definition in fact specifies a topology. There are some examples, which these examples are actually important because they may conclude some things that are not intuitive. For example, the first one, we defined S1 to be these union of sets. Well, as you know, this thing right here was an open set in the Euclidean space, but we said that this thing isn't, and this was in fact a closed set, but that's not relevant. But if we intersect if we define the subspace topology on S1, then you can see that right here the closed interval from 0 to 1 is open in your subspace topology. But as you know, 0 to 1 is not open in the Euclidean space. You can verify this. This is just an intersection with, you can say that it's an intersection with the open interval 0 to 2. So as you can see right here, the closed interval 0 to 1 is an open set in the subspace topology. Another example is again with the Euclidean space, and we have defined S2 to be the sequence of numbers 1 over n, and as you can see, the open sets right here would be discrete points, and this in fact will be discrete space. Now we reached this proposition, which is about open subsets in the subspace topology. As you can see, let me just read the proposition. If S is a subspace of the topological space X. Now let's just assume that U is a subset that is open in S. Okay, so U belongs to your topology, and S is open. Okay, so S belongs to the original topology Tx, then U is open in X. Okay, so this thing reminds me of one interesting property that we had in set theory, which we called transitive property. So if U is an open subset of S and S is an open subset of X, we can say that U is an open subset of X. And the proof of that is actually very simple, and this thing also applies to closed sets. So I want to prove that U belongs to Tx. So U should be equal to S intersected by some open subset in X, and then because S belonged to the topology of X, then, and this thing also belonged to the topology of X, then the intersection of two open sets is an open set, so U is an open set of your topology. The second property says that if U is a subset of S that is either open or closed in X, then it is also open or closed in S, respectively. Well, this property actually needs an exercise, which says that a closed set in your subspace topology is a set that is intersected by S and a closed subset from the original space. So U is just a subset that is either open or closed. Now, I want to show that U is either an open set in your subspace topology or a closed set, which would be S minus U belongs to your subspace topology. Well, if U is an open subset, then if U is an open subset of X, so if U belongs to Tx, then U would be an open subset of your subspace topology. And if U is a closed set in your original topological space, then this thing would be concluded easily. Thanks for watching this episode. I hope you have enjoyed it. Please do not forget to subscribe and hit the like button. Thank you.